So as you can, oh, I went get these lights. Okay, so we have a quiz next class in the last 45 minutes of class. Just want to remind you what it's on. It's on all of the second chapter. Also, maybe you haven't noticed, but I posted a list of topics. I do this for every chapter. I put a detailed list of topics. How many of you have seen those? Okay, good. The chapter 2 list has been up for a while. So there's a posted list of chapter 1 and chapter 2 topics. But this is what you should, that's for the quiz. Also, when before we ended class on Thursday, I talked about some simple gram to mole and mole to gram conversions. Also moles to molecules. And you can expect to see something, 1 or 2 problems on that on the quiz as well. If you remember, we didn't have any complicated chapter 1 conversions on the first quiz. And I'm only putting that as extra credit on the second quiz. Did you understand what I mean? So the more complicated conversion problems from chapter 1, which I didn't put on the last quiz, it will be an extra credit on quiz 2, because frankly, we don't, I'm really more interested in knowing how to do conversions between chemistry things, not like, how much heat it takes to heat a room. And, there's some complicated problems that you get into there that I don't, I want to give you credit for knowing them, but I don't think that they're that important for this course. So they'll be in the extra credit. Okay, so that's what's on the quiz. I also want to encourage everybody. I made my appointment for the updated COVID booster. And they're starting to offer these, like CVS is offering them starting Friday, and Walgreens, it's next week. Anyway, I got COVID a year ago, so I've been okay this year, but I can't wait to get that shot. I feel like I'm going to get it this week, because so many people I know have it. But anyway, it would be a real pain to get it, because then I have to just record classes. I would be able to see my class, so I'm hoping not to get it. What I'm going to give you on the quiz, by the way, I should tell you, of course, I'll give you a periodic table. You will always get a periodic table. I'm also going to give you the polyatomic ions. And I'm also going to give you the transition metal. That's the B group ions. That's this page that has a little periodic table with the B circled. I'm not going to tell you the charges on the ions that form from group 1A, 2A, 5A, 6A, I will not give you. You are expected to know the charges on the ions in groups 1A, 2A, 3, all the A groups. 5A, 6A, and 7A, which is also 1, 2, 13, 15, 16, and 17. I will give you a periodic table like this, see the little one on top of that has the B groups. This is a handout from earlier, but I'll blow this up so you'll have both numbering systems. Anyway, that's what I'll give you. Okay, I'll also give you, of course, Avogadro's number. All right. So I want to move on because we have a lot of important stuff for the rest of this, not just this course, but also Chem 104 today, because we use these mole to mass conversions all the time. So last time, just to sort of give you a little bit of review on what we did, we started to use the masses of elements on the periodic table in gram units, right? So we're getting rid of atomic mass units. We're starting to think about those units in terms of grams. And we found that if we do that, that amount, the amount underneath every element in the periodic table, that amount of any element is what we call 1 mole. That amount in grams is 1 mole, and it has 6.02 times 10 to the 23rd atoms of that element. So if we're talking about carbon, for example, 12.01, if we think about this as grams, this is 1 mole of carbon, and it has 6.02 times 10 to the 23rd atoms of carbon. And this is Avogadro's number. Okay, so we started to think about this number as being in grams. Now, we also went on, and we call this number 12.01 grams is the molar mass of carbon. Okay, then we went on to talk about compounds. I guess I was doing all the talking, really. And calculating the molar mass of a compound. And how do you do that is you add up the correct number, the requisite number of masses from the periodic table of all of the elements in that compound, given the formula. So the formula tells you how many of each of those moles of elements you should count. So you're going to add up the masses of elements, which is from the periodic table, and this is now taken to be in grams. Okay, and this is, you would add them up according to the formula. Okay, so if it's C2H4O2, you would take 2 times 12.01 grams plus 4 times 1.008 grams plus 2 times 16 grams. So this is all really review from last time, and this gives you the molar mass of the compound. Okay, and this has 6.02 times 10 to the 23rd molecules, and of course it is 1 mole. Okay, so I'm just going to review a couple of calculations like this. Oh yeah, one more thing before I do that is I want to remind you, come on, you can do it. Oh well. I want to remind you that, like, for example, this comes out to 60.05 grams. Okay, that this is 60.05 grams per 1 mole. And we can use this, and also the other way, we can do it sort of with the mole on top. These are conversion factors that we use to go from grams to moles and moles to grams. Well, this thing is not so fast today. Okay, so let's just do this example here. So you should always have a periodic table. What is the molar mass of aluminum? You look on the periodic table, the number is right there. It's 26.98. That's what it says underneath aluminum. But that in grams is the molar mass of aluminum. So that's the first thing. How many moles are in 87.2 grams of aluminum? I never think, do I have to divide or do I have to multiply? I simply put the conversion factor in the correct way so as to cancel grams. If you put it like that, you're dividing, but you just put it so that the grams cancel and you end up with moles and you get the answer. Okay? If I also asked you, okay, so then we want to do an example the other way. 1.17 times 10 to the minus 2 moles of Al. And I want to convert that to grams. I want moles to cancel. So I put 1 mole on the bottom, 26.98 grams on top, and I get 0.315 moles. Okay, now we did do a different type of problem also. We were able to go from moles to atoms. So what if I ask this additional question? How many atoms is this? Is 0.315 moles. So we would start with atoms, moles. And once again, okay, now here we have to use, what would we put in here? What goes on top? 1 mole will go on the bottom to cancel moles, but what on top? The number of atoms per mole, and that's 6.02 times 10 to the 23rd atoms per mole. So I can use this conversion factor like I've used it to solve this type of problem, or I could flip it if I want to go from atoms to moles. So let's do this, and we get 1.90 times 10 to the 23rd atoms. And you shouldn't be shocked at that large number of atoms because it's a pretty macroscopic sample, 0.315 moles. It's a pretty big sample. Okay, so that's that number 1 there. And now if we go, and now we already calculated the molar mass of C2H4O2. So we would write it as 60.05 grams per mole when we write a molar mass. So what is the molar mass of this? 60.05 grams per mole. So again, we get to use the 60.05 grams, 1 mole, and we can also use it flipped the other way to get 1 mole over 60.05 grams. So how many moles are in 186 grams? What am I going to put on top? And what am I going to put on the bottom? 1 mole, 60.05 grams. How did I get this number? I got it from adding up 4 carbons, 6 hydrogens, 1 oxygen, right off the periodic table. Okay, and this comes out to, hold on a minute. I think I screwed up something here. I guess this was this is not C2H4O2, duh. Somebody could have gotten a gotcha there, 4 carbons, 8 hydrogens. We didn't do this one, so I got to do 4 times 12.01, 8 times 1.008, 1 times 16. Yeah, it's not 60.05. Sorry about that. It comes out to 72.10 grams per mole. That is the molar mass. Sorry about that. Okay. And so that comes out to 2.58 moles. Okay. And the next question is, what is the mass of this number of moles? And now we use it the opposite way. We put grams on top to be able to cancel moles. And we get 0.155 grams. So these are some, relatively, I hope, straightforward examples. Are there any questions? So Avogadro's number is the number of anything in a mole. It's 6.02 times 10 to the 23rd anything, like a dozen. You could have a dozen eggs, you could have a dozen rabbits, you could have a dozen incandescent light bulbs, you could have a mole of anything. So when we write Avogadro's number in general, we might write particles per mole, because we're generally talking about particles, not eggs, when we're talking about a mole. All right. So we can say how many molecules are in a mole. Okay, so let's say I want to figure out how many molecules is in 2.58 moles. So let's go down here. How many molecules is this? So we'll start with the number of moles. And now I'll put 6.02 times 10 to the 23rd molecules per 1 mole to cancel moles. And again, it's going to be a huge number. Okay. So one more thing I'd like to talk about before getting to the number 3 there, is that let's consider C4H8O. Let's consider this a little further, okay? So we know that one C4H8O molecule has 4 carbon atoms, 8 hydrogen atoms, and 1 oxygen atom, okay? Now, since a mole is just a certain number of molecules, it follows that 1 mole of C4H8O has 4 moles of carbon atoms. Okay, so the proportions are the same. 8 moles of hydrogen atoms and 1 mole of oxygen atoms. So it's like whatever we said for molecules, really the same thing goes for moles. Okay, let me just get a little more room here. Okay, so the atom ratios in a molecule of a compound give the mole ratios of elements in a mole of the compound. They are one and the same thing. It's the atom ratios in a molecule of a compound, of course, give the mole ratios of atoms, of elements in a mole of the compound, okay? So here we have 4 atoms of carbon to 8 atoms of hydrogen to 1 atom of oxygen. It also means that 4 moles of carbon goes with 8 moles of hydrogen and 1 mole of oxygen in 1 mole of C4H8O. This is in 1 molecule, which makes it kind of nice because, you know, we're talking about moles, which is a handleable kind of macroscopic amount, and it's the same ratios, okay? So in 1 mole of C4H8O, we just did this, 4 moles C, 8 moles H, and 1 mole O. So then we have a 4 to 8 to 1 mole ratio. Okay, we'll see these mole ratios all the time, which is why I'm trying to give you a good, you know, do you feel like I'm going too slow here, or are you glad that I'm going through this? Okay, all right. So activity 2, just a little more examples. So the first 2 problems in activity 2 are with just an element, copper. And I think that you can do these at home, and you can just go on now and do problem 3. So I'd like you to do if you're really insecure, you're not ready for a compound, you could try doing 1 and 2, but I think that everyone here should go on to 3 and leave those for home. Okay, so we have ammonia. That's a compound, consists of nitrogen and hydrogen. And here's the number of moles. It's asking for the mass. Okay, and then it's asking how many molecules are in that sample. This was the handout I gave out last week. It's right here. This is the activities for that chapter. And then when you're done with that, go on to number 5 and number 6. And by the way, I have 2 problem 6s on the second page. Why don't you change the second one to problem 7? So it's a kind of a typo there. All right, and so we do some of these and I'll go over some and then we can go on to the next thing. If you have questions, now would be a good time to ask them. And I am collecting the special problem from Molecules, you don't go from mass to mole back to the number of moles. Yeah. Taking that number, yes, yes. Yes, yeah, this isn't, so the way problem 3 is written, it first asks you for the mass, and then it asks you for the molecule. But that doesn't mean that you use the math to get molecules. What do you use to get molecules? Sorry? Yes, but it's, you start with the number of moles, so you go back to the number of moles, and then you use Avogadro's. Yeah, you're always going from particles to moles, moles to particles. It's harder to go from grams to particles.
Yeah.
Yep, and that's how you do it, yeah. You have to get the mass also. This way for mass. Yeah. Oh, yeah. Okay, so this is the molecule. That's right. Yes. Or use dimensional analysis, don't even think about whether you're multiplying or dividing, just get the units right.
Right. So I think as
What, a million zeros after the 141?
So the ones.
All right, so that's 360, and you gave me an answer that's 260. 0.04040, 260, so it should go there. This time. Can it be either? What did you get, 0.0400, what did you get?
So I got physical,
039, yeah,
so I got 4.3.
okay, so you would put 0.0398. No, you would put 0.0400. No, 0.0399, yeah, this 8 rounds to a 9, and you keep those 3 digits for 0.0399. Okay. That's the right answer. I mean, this is the right answer. It's the right answer. Well, thank you. This one. Same number.
So we had.
I'm gonna go over it, but not just yet. Yes. You start, you write what you have. Then you use the whole ratio. That way you never get it wrong. So I want to say it. I'm gonna show it. Going, folks. Keep going, you can actually go all the way to this. 8, and 7. Oh, it's been at the decimal. That's round that 360. You're at 399. The amount of the from the 3 keys. Where? Yeah, no. The math. No, that's great. No, it's just bold. Yeah, out there. There was and I just saw this. Yeah. This year. So I would. Don't go for grants. Wait. That's what I can see. Go down and go with them. It's that. I don't know. I guess it's. That was like, you don't go, that's not full, that's great. That already is so that's credit. It's actually, I stopped. There. You don't find it all. Oh, that's full. When you go to get the number of molecules, don't start it. This, I'm sorry, this is actually France. France, so you need to first do. Oh, well, you could, go directly. Just, you know, I did, like, I'm telling you, better correlation.
Oh.
Then take this.
I mean, oh, yeah.
So it's one more. Yes. Okay. One again. I'm like, why is it? Yeah. There's no direct conversion. Yeah. Now I am. I was overthinking, and now I don't need. Figure it out one more. We're gonna start with. Start with. Who am I supposed to call? Oh my God, worry. It's just a very, you see, only cancel, it's might discourage this, and then you're just focusing on buying it, get it on so glad. That really makes it feel. Right, I would have written this first and then that, but yes, that's. Well, that's. Did you do this then? Okay, so you did this right, but you see, you could have done, could have done this, and not bothered to multiply it, and then just put this ratio next to it. Right, and then put this. Yeah, you could just, yeah, there's no reason, not everything has to be in parentheses. This is just. And we start with the number of grams, it's not related. So you could. Yes, that is. But you can use. 1.0 of this. Your grams. It would be grams and right. Think about it. Okay. I got it. Did you get your question answered? I'll be right back. All right. It's because this number is not a losing number. What should you do to this number to get? Yeah, you're really multiplying. I think this could be a sound again. We do that starting with any number, right? Starting with this, where we do the same ratio. So we call that a ratio. Who's that all? Oh, really? Yeah, I'm gonna go over this because I can see a lot of people have it. But. Yeah. That's, we call that a whole ratio. They use that over and over. All right, I gotta go over some stuff. Okay, so. First, in number 3, ammonia, what did you have to start by doing? Well, okay, first of all, I'm asking what is the mass in this many moles? So you need to calculate what? What do you call that total? Right, we need the molar mass of ammonia. So 1 nitrogen is 14.01
3 hydrogens is 3 times 1.008. And so we can add that up. I'm just gonna show you what the result is, and that's 17.03. Now, I noticed while I was walking around that a lot of you use 17. Okay, 17 has only 2 significant figures. This problem has 3 significant figures here in the number you're given. You should never, never limit the sig figs of a calculation by taking a molar mass to only 2 sig figs. The molar mass is known to many sig figs, so you should always have the same number or even more sig figs in the molar mass than you have in the number that you're using in the calculation. So you'd start with 2.34 times 10 to the minus 3 moles of NH3. And I know that writing NH3 is a pain in the neck, but for beginners, you may want to be very clear on what you're calculating and what you're using, and that is moles of NH3. And this is 17.0, oops, I was writing it in the wrong place because I know it's grams per mole of NH3, okay? As soon as I wrote the 17 grams on the bottom, I knew it was wrong because it wasn't going to cancel moles. So I flipped it, okay? And that gives you 0.0399 grams. I kept 1, 2, 3 significant figures. If your number was slightly different, it might have been because you didn't use this to the full significance, okay? All right, so that's the number of grams. But how many molecules is this? When you calculate molecules, you got to start with moles, right? You can't go from grams to molecules. There's no direct conversion, okay? So you would not use the number of grams that you got in this calculation for the next part. You would start again with the number of moles. And now you'll use Avogadro's number. And that's molecules in 1 mole. And now moles cancels. And you're going to get a pretty gigantic number here. I saw this number a lot while I was walking around.
So what is the 0.0399 what you use in math?
That is the mass. That's the answer, yeah. You don't use it to do anything else. That's the end of the calculation.
That's not the same as the 17.3.
That's the molar mass, which you get over here, okay? Grams per mole, this unit means grams per 1 mole, okay? Any other questions about this problem? All right. What, I didn't put number 4 here, I guess. Oh, 5. I went from 3 to 5. Oh boy, that's great. Okay, how many, this is like now I'm talking about something a little bit different, but also something we went over. If we're talking about a molecule of water, how many oxygen atoms are in that? 1 molecule of water has 1 oxygen atom. So 1 mole of water has 1 mole of oxygen. So extending that, if you have 4 moles of water, and each mole of water has a mole of oxygen, then you have 4 moles of oxygen and 4 moles. So what this is pointing out is that atom ratios in a molecule are the same as mole ratios of elements in a compound. Okay, so continuing with this, yes? Because a mole is a fixed number of atoms, so it's all proportional. Yeah. How many atoms of hydrogen are in 1 molecule of water? Well, the subscript tells you there's 2, all right? So how many moles of hydrogen are in a mole of water? 2. It's the same. How many moles of hydrogen are in 3 moles of water? calculate, multiply 2 times 3. You have 3 moles of what? But, you know, if you don't like to do that kind of math and, you know, in your head, I give you a nice method that we use over and over again. If you have 3 moles of water, this is the way to think about it. You have 2 moles of hydrogen for one mole of H2O. And you can see your moles of water cancels, and you're just effectively multiplying 3 times 2 to get 6, right? This we call a mole ratio. And we use it over and over and over again, not just in this chapter, but in many, many, many of the chapters in this course and in the following course. We use it to relate moles of an element in a mole of compound. We use it to relate moles of reactants to moles of products, moles of reactants to other reactants, moles of products to other moles of products. From the chemical equation, we'll do that next, a little later, but it's something we use over and over again. So you use it, get used to it. You know, it's tempting, oh, just do it in your head, but there are examples that are not so easy. And so here again, you're just really multiplying by 2. And then you could even do it with numbers that aren't so whole, you know, here. If you have 2.75 times 10 to the negative 4th, sorry, moles of water, again, it's 1 mole of water to 2 moles of H. So you're basically just multiplying by 2. And you get 5.50 times 10 to the negative 4th. Okay, but just multiplying by 2 because there are 2 moles of hydrogen per mole of water. Okay, so some of you, very few of you, I think, got to problem 7. By the way, if you didn't finish, you know, everything you didn't finish, like 1 and 2, you really should do at home. So here we're going to use these tools that we just learned about converting grams to moles. We're starting with a sample of water. This is a water sample weighing 35.17 grams. We can start with that, and what we are going to end up with here is how many grams of hydrogen are in that sample. So you have a sample of water. It really contains hydrogen and oxygen bonded together in a certain way. You have a certain amount of mass comes from oxygen and a certain amount of mass comes from hydrogen. So this problem is asking, if you take A, B, and C together, if you start with a certain mass of H2O, what is the mass of hydrogen in that sample, right? How do you do that? What is your strategy for doing this type of problem? So we want to go from the mass of H2O of a sample. We want to go all the way to the mass of hydrogen in the sample. So what we know how to do is we can convert the mass of hydrogen to the moles, sorry, mass of water to the moles of water. How do we do that? What do we use to do that? What is the thing you have to calculate to do that? Molar mass, molar mass. It needs the molar mass of water to do that. Once you have the moles of H2O, you can find the moles of hydrogen using what we just talked about, that mole ratio of hydrogen to water, okay? And then finally, now we could find the mass of hydrogen in the sample, which is grams, and we'll use the molar mass of hydrogen, which we get right off the periodic table, okay? So the first step would be to convert the 35.17 grams to moles of water. Okay. So I don't know if you've worked on this, but I'd like you to work on this problem for a few minutes, like 5 minutes or so. Okay, see how far you can get. Then I'll go over it. And if you have more questions, ask them.
You can ask me something about a previous problem.
So annoying. I don't know, I just want to know what time it is, and my watch keeps telling me, you know, how many steps I did and how many this and that. I'm like, what time is it? Kind of crazy. All right, did you calculate the molar mass of water? And what did you get? Right, you could round that to 18.02 if you wanted to, that would be okay. Or you could use 18.016 grams per 1 mole. And this is of H2O. So this is a very typical calculation. We've done quite a few like this. Okay. So now, this is very much like these problems we did here, where we have the moles of H2O, and we want to know how many moles of hydrogen. So we use that mole ratio. So we basically just multiply by 2. What?
This is 2 moles of hydrogen per 1.
Oh, God. Yes. You got a gotcha there. I know, it's great. It's not good for me, but it's good for you. Okay. All right, yes, I hate making mistakes. Okay, now when we have the 3.904 moles of hydrogen, how are we going to get that to be grams of hydrogen? What do I put here? What goes on top? Use your handy periodic table, because you need the molar mass of hydrogen, which is the number written right underneath the H, right? That's a 1.008. It's going to look a lot like, you know, it's like multiplying by 1, but a little bit different. Moles of hydrogen cancel, and we get 3.935. You see, it's a little bit different from the moles because it's not 1 exactly, it's 1.008. Now, this special problem, this is a special problem. I'm not going to do this here, but 7D, which is 6D on your piece of paper because it has the wrong number. I want you to do this all at once. What does that mean? That means that instead of doing 3 separate problems here, I want you to start with 35.17 grams of hydrogen. I made a mess of it now. Grams of water, sorry. Convert it to moles, but don't write the answer down. Just use the parentheses. And then, if you were to multiply it, you would have moles of water. But remember, you could write the mass down, then you could have different sets of parentheses to get the final answer. You know what the answer is going to be, but I want to see you set it up this way. If you give me the answer, but you don't set it up in this way, I'm not going to give you the special problem credit. The special problem credit is to try to get you to do it all at once. So here you'll have your grams to moles of H2O. Here you'll have moles H2O to moles of hydrogen. You're not going to put this is just telling you what conversion you'll need in there, what that conversion needs to do. Finally, moles hydrogen to grams of hydrogen. Okay, so that's what everyone understand what I would like for this special problem. It's very simple to do, I think. You know the answer, but I need to see you do that and cancel the units the way they should. That's a very smart way to do this problem. So that's why I'm giving you a special problem credit for it. One more thing with this set of problems is that when you do this, you get 3.935 grams of hydrogen. So we know that there is 3.935 grams of hydrogen in 35.17 grams of water. So what we do a lot is we formulate something called the percent by mass, or the mass percent of any elements in a compound. And it's just the way you calculate any percent. We know that the entire mass of the water is 35.17. That's the total mass of the sample. And we know that the mass due to hydrogen is 3.935. Okay, grams cancels, and we just multiply this by 100 to get a percent, and comes out to 11.19% hydrogen. And of course, I could take 100 and subtract 11.19, and I'll get the 88.81. That's the percent oxygen. So taken together, 88.81, sorry, 8.81% O, 11.19% H. This is the percent composition of oxygen and hydrogen in H2O, okay? And what that means is it's the percent by mass of each of those elements in the compound. That we call it percent composition. Okay, now, what I need to tell you about next is how to find formulas. And you're going to be finding a formula in lab today. By the way, this week lab is still in the same old place, but I think that next week we're going to have lab in the lab. So that'll be, your lab teacher will tell you about that. So, so what you need, the lab today is about finding formulas, okay? And what you need to think about is that we have an ability now, we can relate mass to moles. You know, we know how to do this now, very excited about this. Okay, but what that allows us to do, it leads us to finding formulas. And the reason we can do that, of course, is because we can convert mass to moles. And if we know the moles of each element in the compound, then we can tell what the formula is, because the atom ratio of atoms in a molecule is the same as the mole ratio of elements in a compound. So this is just a little write-up telling you one method that's used to find formulas. But it says I'm going to do an example. So I'm going to just do an example to show you this method. And then I have an example for you to do. So let's suppose this is for you to do, not the one I'm going to do now. Now, here's my example. So here's the example. Suppose a compound is analyzed. A lot of times we send samples out. You synthesize something in the lab, you don't know what its formula is. You want to find out what its formula is, you send it out to be analyzed. We call it elemental analysis. And what happens, what it comes back with is it can tell you in various ways, but one way is it gives you the grams of each element in the compound. And this allows you to figure out the formula, okay? So let's suppose this compound is sent out for analysis and it comes back that 5.33 grams of the compound is carbon, 0.896 grams is hydrogen, and 1.78 grams is oxygen. So given the masses of each element, how are we going to find the formula? So what do you think about this? What would you think you would do with each of these masses? Because formula, remember, the atom ratios in a formula are the same as the mole ratios in that compound. So are you saying, and what's you mean one, what do you mean one carbon? So in other words, I think you're telling me to convert this number to moles. That is what you do, yes. You find the number of moles of each of those elements. So we're going to find the moles of each element in these amount of grams. So for carbon, right, this is the molar mass of carbon from the periodic table. Okay, when we do that, we get 0.444 moles of carbon, but we can do it to all of those numbers there. 0.896 grams of hydrogen. Again, we look on the periodic table and we see 1.008 grams per 1 mole hydrogen. So we get 0.889 moles of hydrogen. And when we do this with the oxygen, 1.78 grams to moles. Grams cancels. We get 0.111 moles of, so we really have a carbon to hydrogen to oxygen ratio of 0.444 to 0.889 to 0.111. But when we do formulas, we don't use decimal numbers. We don't use fractional numbers. We use whole numbers. So we need to put this ratio in terms of whole numbers. So this is the mole ratio of C to H to O, but we must put it in terms of whole numbers. How do we do that? Blast this thing today. Okay. All right, so we want to keep the ratio the same, but we want it to be in terms of whole numbers. And the easiest way to do this, anybody have an idea? Yeah. Well, if you multiply by 1,000, this is what you get. So, I mean, you're not going to write C444H88901111, right? Because you always have to reduce it, right? So the thing here is to reduce it. And I didn't hear you. I mean, you could multiply by 1,000, but that's not going to get you very far. The thing to do is to actually divide by the smallest number, right? When you do that, this becomes 1 here. That's what you want. You want a nice whole number. This is 8.01. And this is 1.00. So when you do this, you know, if you get numbers that are very close to whole numbers, you're done. You know, this is 1. Wait a minute. Yeah, I'm sorry, this is 4, not 1. Yeah. So it's 4 to 8 to 1. So that tells you it's C4H8O, that this is the formula. Okay. So what I would like you to do is there's a problem. I'm going to come back to this because this is only what we call a simplest or empirical formula. I'll come back to that. But I want you to do this problem. That page I gave out, put HOD on top of it. This is going to be the handout of the day. Okay. And what you want to do is start with the masses of each of these, and you want to convert it to moles. Then you want to find the mole ratio. So this is first. Next, you find the mole ratio. And then third, you put it in terms of whole numbers by dividing by the smallest number. Okay, so that's the handout of the day today. So don't forget to put your name on it and hand that in before you leave. You know, I post these, right? But I really do need to move forward a little. Okay, so I had some more to tell you about these formulas that you can get high. Whenever the talking goes up, I know it's because most people have finished the problem. So I'm going to move on. So the answer that you got for the handout of the day, also this answer that I got here from this last problem that I did, this it's definitely called a formula, but notice that the way I wrote this formula was I simply looked at the mole ratio. Now, if I had C8 H16O2, can I just have your attention here? Okay, this mole ratio, 8 to 16 to 2, is the same as 4 to 8 to 1. So when I get this answer for what the formula is, when I get this formula here, that only gives me the simplest formula. So this, with this data, with this information, you can only get the simplest, in other words, the reduced formula. There are compounds with, you know, much more complicated, like this one, C8H16O2, has the same mole ratio, but it's a different formula. You see that? So we have a term for that. We have a term that we use. It's called the empirical formula. So this method can only give what we call the simplest or the empirical. Empirical means from experiment. If you use experimental information for the mass of each compound, you'll only be able to get the empirical or simplest formula. Okay, so going back to C4H8O, it could be C8H16O, it could be C12H24, oops, O2, O3, all these have the same mole ratio. Okay. So, okay, so I want to give you some examples of molecular formulas and empirical formulas. So if the molecular formula, here's an example. If it's here, I'll just use this one, C8H16O2, then the empirical formula is C4H8O. I can't make it any simpler than that because it only has one oxygen in that formula. What about, here's a much sort of easier one, H2O2. What would the empirical formula be corresponding to H2O2? What's the simplest formula? There'd just be HO, right? Ho, ho, ho. N2O4, dinitrogen tetroxide. What's the simplest formula? NO2, yeah. Yeah, I think that's what you said. C6H6, that's benzene. CH, that's right. So if you were given the masses of carbon and hydrogen in this compound, you would only be able to say that the formula has a 1-to-1 ratio of carbon to hydrogen, that the empirical formula is CH. What about glucose? What would the formula, the empirical formula be for that one? Right. That's right. CH2. Oh, so if you know the empirical formula from one of this method I just showed you, how do you get the molecular formula? So to get a molecular formula, you need other information. And in particular, you need to know the molar mass. Okay? So if we let's see. So I'll talk to you about that with our next example. We'll do it in an example. So I just want to point out to you that I gave you this handout. This is part of the packet. And it has to do with determining an empirical formula from percent composition. I don't want you to read that now. You can, it's a longish handout, gives all the steps, but I'm going to do an example here that shows you how to do this. So I have an example, and so you could figure out formulas from being given percent composition instead of being given the mass of each element. This is an example of getting formulas from percent of each element or percent composition. Okay, so in the example I'm going to do, if I have a compound, is known to be 69.52% O and 30.48% N. So it has N and O, and it has these percentages. The question is, how do I find the formula? Okay, so the first thing that you do in a problem like this is to pretend that you have a sample that's 100 grams. Now, why would you pretend a thing like that? To pretend you have a 100-gram sample. Why would you pretend you have a 100-gram sample? Yes. And why are they easy to work with? How many grams of O does that mean you have? That's right. Because you would have 69.52 grams of O in a 100-gram sample, because the sample is 69.52% O, okay, and 30.48% grams of N. I don't know why it takes so long to erase, but it does. Okay, so if you have a 100-gram sample, you know the number of grams of O and the grams of N, and you could go ahead and convert this to moles using the molar mass. Okay, so I convert this to moles. And here, oops, see, I wrote it the wrong way. So I'm gonna wait for the pen to respond. Grams, so this is just the numbers off the periodic table. And this comes out to 2.176 moles of N. So that's the first thing you do, is pretend you have the 100-gram sample. Then you convert grams to moles of each element. What's the third thing that you do is you formulate a mole ratio. So I have 4.345 moles of O to 2.176 moles of N. Okay, but I want this in terms of whole numbers. So what do? Right, I divide by the smallest number. So that it becomes 2 to 1. So this formula, this is N, so N we usually write first. So be NO2, because this is for O and this is for N. Okay, there's lots of compounds with nitrogen and oxygen. So this is the empirical formula. So what's another formula? Oh no. Here we go again, right? Is it dying? No. See how long I'm going to put up with this. Wow, that's great. I want to look at some pictures. Okay, so we did all this already, right? Okay, so if that's the empirical formula, then there are all kinds of possibilities for what this formula can actually be. So what are the possibilities? These are the possible molecular formulas. Okay, we could have NO2. What's another one we could have? N2O4, N4O8, we could have N3O6. These are all possibilities for molecular formulas. Okay, so how do I figure it out? Well, I need to be given the molar mass. Okay, and let's suppose you're given that the molar mass is 92.02 grams per mole of the compound, the unknown compound. So what we do is we take the empirical formula, which is NO2, and calculate its molar mass. And when you do that, you find you have 14.01 for the nitrogen, and you have for oxygen 2 times 16. You add that up, and it comes out to 46.01 for NO2. Okay. So the molar mass is 92.02. The molar mass of the empirical formula is 46. So how many empirical formulas are there in the molecular formula? The quickest way to do that is to take the molecular weight, the molar mass of the compound, and divide it by the molar mass of the empirical formula. And you'll see that you get 2. Okay, so what did I just do? You're given 92.02. That's the molar mass of the actual molecular compound. You also can calculate the molar mass of just the NO2, the empirical formula. And now you could see how many times that empirical formula goes into the molecular formula. Okay, and you see it's twice. So that tells you that there are 2 NO2s, really. But you wouldn't write it like that. You would write it as N2O4. So I guess I would say that the last step is to divide the molar mass of the compound by the molar mass of the empirical formula. Okay, and this is written up in that handout with an example next to it if you didn't catch everything that we did right here. Well, yes, we have. And we're just starting to work with it. Mass, we started with mass percentage. That's where we started with, remember? And then we assumed we had the 100 grams.
But we had to, in another example, find.
No, I haven't done that yet.
Oh, that's good.
Yeah. So I would like you to take and look at activity. This is, what time is it anyway? Oh, we got time. So activity 3, the back of the page, number 4 has a problem. This is a, let's see. This is a special problem. So you can start it here, get your questions asked, and finish it at home. Okay. And you're supposed to determine, let's see if I have it here. Yeah, here. Oh, just go down to this. Determine the empirical formula of a compound given these percents by mass. Okay. So you're given 49.48% carbon, etc. It has 4 different elements. So using the handout and what I just went over, right, you start by assuming you have 100 grams and convert grams to moles. Okay, a few more steps. But just start that. And I want to call the attention of people. Well, I'll do it in a few minutes. So just work on that for a little bit. Just get it started. Better Google that. What else was in my office the other day with that? I should have Googled it. Wow. I thought there, of course. Oops, not here Monday. So I'll collect this one on Tuesday because I want you to study for the quiz for Thursday. Anybody have a question on, anybody stuck yet or? Okay, I do want to move on and tell you a few more things. Oh, first of all, I have another special problem here. This is a more difficult problem. This deals with combustion analysis, and I don't recommend you do this unless you really want to do it, like you really like this stuff. And but this diagram kind of tells you how you get this information, like how you get the mass or the percent of elements in a compound. And so that for that reason, it's pretty interesting. So what's done here is that the sample is burned in oxygen. Okay, so the sample is weighed and then it's burned. And you put there's something in here that absorbs water. So you weigh the water absorber before, and then you weigh it after it absorbs the water, and you can get the mass of the H2O that's produced in the combustion from this, which gives you the mass of hydrogen. Similarly, this carbon dioxide absorber, which you can weigh before and after, gives you the mass of CO2, which ends up giving you the mass of carbon. Okay, and then you could add up these two masses, subtract it from the weighed sample, and then you get the mass of oxygen. And from that, you can get the formula. So this is a more complicated problem, which you are not responsible for knowing how to do. And I don't even think you should do it if you're already confused. Okay, so but if it's like a challenge problem. Okay, if you don't want a challenge problem, then don't do this special problem. Okay. So anyway, I want to go over a couple more things. I have a little time. So let's go to activity 3, which you're already on, but I want to look at number 1. And this is what somebody just asked me. How do you find the percent by mass of any elements in a compound? And so what do you do to do that? So whenever you're asked to find the percent by mass of an element in a compound, you start by figuring out the molar mass of that compound. So let me show you. In this example, we have C2H5Cl. So how do you get the molar mass? You simply take 2 carbons, right? That's 2 times 12.01 grams per mole, or grams, okay? That's 24.02. And then you have 5 hydrogens. So we've done this before. That would give you 5.040. And then we have 1 chlorine. Chlorine has a molar mass of 35.453. So we would add that. And then we would get the total molar mass of the compound as 64.51 grams. So how would we find the percent carbon in this compound? What we do is we look back to the mass. Oops, I just crossed it out when I meant to highlight it. Not so good. So we take the mass of carbon, which is 24.02, and we divide it by the total mass of the molar mass, 64.51 grams. So this is the grams of carbon divided by the grams of the compound. And we multiply that by 100. So that comes out to 37.23%. So we literally add up the molar mass, figure out how much of that molar mass was due to carbon, which you actually do as you, along the way, as you're calculating the molar mass, and divide that number, the highlighted number, by the 64.51 to get the percent. This is the percent by mass of carbon. Okay. Another type of problem that you could run into is if you're given a mass of compound and its formula to find the mass of any element present in that compound. Now, do you remember when we did problem 7, A, B, and C for water? This was from activity 2. This was a problem like this. And remember, I told you you could do it all at once, right? Let me show you what I mean by that. So we want to know the number of grams of sodium in a certain mass of this compound. So what you do is you start with the grams of the compound, Na3, PO4. Okay, so now I'm going to convert that number of grams to moles. So the molar mass of Na3PO4 is 163.94. Okay, the way you get that is 3 sodiums is 3 times 22.99. You have now in a PO4, you have 1 P and 4 O's. That phosphorus has a molar mass of 30.97. And oxygen, what's the molar mass of oxygen? 16. So we add all this up. The first one is 68.97. The second one is 30.97. And then 64 for the third one. And that's how we get 193.94. And I always like to write what I'm talking about in here. 1 mole of the compound. Oh, it's 63, yeah. Who did that? All right, I owe you. Okay. So now I have, if I cancel grams, I have moles of Na3PO4. To find the moles of sodium, right? How much, what is the, I need to go from moles of Na3PO4. Oh, forget it. I can't do this anymore. Bye, have a nice lab. I'll start here next time.